From last lecture, just to summarise, what we were doing was we were looking at the climate change over the last kind of century, maybe a little bit longer, and seeing if we could explain all of this variability. So all of the change in temperature from pre-industrial periods to the modern, and also some of the wiggles, some of the ups and downs, some of the kind of the deviation from a nice smooth temperature change. And part of that was due to things like sunspots. Okay, but we showed that the overall trend, okay, is not due to increase in solar activity. Some of the wiggles might be, just like some of the wiggles are caused by changing in cloud brightness. Okay, and a large part of the wiggles up and down are caused by this internal variability within the climate system, particularly El Nino. And that does that still, I forgot. Okay, so what we're going to do now is going to be looking at basically some of the evidence for attributing the climate change to various forcings and what's going to be happening into the future. So I had an email from someone which I didn't respond to, which I'm sorry about because I was a bit busy, which was about what are proxies, because I mentioned them a lot and it was maybe a little bit confusing. So this is what kind of proxies are. So rather than directly measure temperature or precipitation or some environmental parameter in the past, we can't do that because the past no longer exists. Well, kind of technically, it's a philosophical question, does the past exist? But we can't go back and make those measurements. So what we have to do is look at things that were formed in the past, so things like tree rings, ice cores, coral, sediment records containing pollen, stuff like that. And we've got to look at those things, okay, and they will tell us something about the temperature or the precipitation at the time. Okay, so it might be the width of tree rings, might tell us how warm or wet it was. The isotopes preserved in ice cores might tell us how warm or cold that ice core was formed in. So we've got this range of records to look at, and we've got a combination of proxy measurements for looking quite far back in time, but we've also got covering the last kind of 100 years or so instrumental records where people actually go out and read a thermometer from a Stevenson screen type weather station, or maybe some ocean buoys measuring temperature out in the ocean. And then over the last kind of maybe 30 years or so, we've had satellites that have been measuring the temperature kind of over a much wider, broader geographical range, which has basically given us much more detailed information. And this is kind of how it all kind of fits together. And this is a bit of a horrible plot, but this is a combination of that proxy evidence and the modern instrumental records. So the instrumental records are in black on here, so this shows the temperature increasing over time. I should just point out that this top figure is data just for the northern hemisphere. The southern hemisphere data is down here, and the whole global average temperature is here. So we're focusing on the northern hemisphere because this is where the most data is in terms of both people actually measuring it with thermometers, okay, because there were more people with thermometers in the late 19th century than there were in the southern hemisphere. And also there's more proxy evidence in the northern hemisphere. And this is partially because there's more land in the northern hemisphere, so there's more places where scientists can go to find some proxy evidence. But there's also more scientists in the northern hemisphere. So there's this bias that scientists go out and study areas kind of near them rather than in the southern hemisphere. So there's more data in the northern hemisphere. All of the wiggles on here are, so the different colours refer to, I think, different combinations of either land and sea data. So I think the thick lines are where they've just got land data, and the thin lines are where they've got including data from the ocean as well. And then the different colours are whether they include the tropics or just the high latitudes or not. And the detail of that doesn't really matter because broadly all of the wiggles kind of look the same in that there might be some variability in climate throughout this period, but it kind of stays within this kind of plus or minus maybe ½ degree Celsius. Okay? It's only when we get into the modern industrial period do we start to have temperatures that are basically shooting off outside of the variability that we've seen in the past. So one line of evidence that the warming that we're seeing now is not natural is that when we look into the past, we don't see climate change like we're seeing now in the past. Okay. So moving into the instrumental period, one of the maybe I guess the less rational criticisms of the way that we construct our climate history is that there are a bunch of different research groups that work completely independently, and they take the same or similar data sets to produce this kind of record of temperature through time. Okay? And there's this kind of this argument that basically this is the one of them. This is by a group in the Hadley Centre, which is based in the University of East Anglia, and they've just basically taken wherever there's one of these pixels, that's where there is some data. Okay, and this is a map of the temperature in basically the temperature in 2012 minus the temperature in 1901. So it's basically 100 years of temperature difference. So you can see that these give positive numbers mostly, so this means that it's warmer now than it was in the past. Now these bottom figures are using exactly the same data, okay, but there's a lot fewer gaps in the data. So you can see regions over the Southern Ocean, in Africa, South America. There's no data on that plot because, I mean, we know what the temperature is there now, but there was nobody out there measuring the temperature in 1900, so we don't have anything to compare it to. Whereas these groups here have basically, all they've done is they've taken the data that exists and they've extrapolated it over areas where data doesn't exist. And so you might expect if they're extrapolating kind of across into regions where we don't have data, you might get kind of different answers. But it turns out that that's not true. So if you basically plot up the temperature records of all of the different approaches to working out the average global temperature, you get the same answer over and over and over again. Okay? And that's because the climate change in one region on the Earth is closely coupled to the region just next to it. So although there's lots of spatial patterns in climate, because we've basically got enough geographical spread of data, we can fill in the gaps, and we do get a really, really robust estimate of what the temperature has been changing over the last 100 years or so. So there is no question whatsoever that it is a lot warmer now, over a degree Celsius warmer than it was in the pre-industrial period. Okay, so that's a fact. Okay, so moving on now from basically accepting that change in temperature is real and is anomalous in terms of geological history, we want to go on and say, can we actually attribute that warming to our activities? And we covered this this graph a little bit in the lecture yesterday, but this is basically looking at all of the different forcings. So volcanic forcings act as sporadic coolings. We've got, and we've also, you can see here that there's kind of like a little bit more forcing in the late 20th century, and that's largely due to this increased industrial activity that's pumping out sulfate aerosols. We've got solar forcing and carbon dioxide, or basically all of our greenhouse gas forcing. Excuse me. So we can then look at the proxy data. So that this grey curve that's on the background of this plot is effectively the data from the first plot I showed you. It's that proxy reconstructed temperature. And the two sets of lines, the thick lines and the thin lines, are the same sets of climate models that have been run, that basically one set, the thin lines, excludes anthropogenic carbon dioxide forcing. And we can see that without that forcing, we can't explain the temperature record. So that means that to explain the temperature record, you need to have anthropogenic carbon dioxide forming a big part of the reason for change. So, so these are those forcings that are going to go into those models. So we kind of covered this a little bit the other day. So carbon dioxide is the most important, okay, most significant contributor to the radiative forcing in our emissivity term, in our temperature of the surface equation. Methane is also important, both in terms of its direct greenhouse gas warming, but also for the chemical reactions and products of those chemical reactions that happen in the atmosphere. So the conversion of methane to CO2, the effect that it has on ozone, just like CFCs, so they have a very strong greenhouse gas effect, but they also have an effect on ozone chemistry, so that also affects the greenhouse effect indirectly, and aerosols as well. So when we combine these all together, we get this kind of forcing that we need to have to explain our temperature records. So this is a kind of a simplified view of that, that model comparison here. So the red line on this plot is the global temperature recorded by thermometers, averaged over the globe, all that kind of stuff. So that's this red line here, and you can see it's got warmer. Now the grey line on here is basically a collection of model experiments, and they've kind of averaged them all together, and they've got some range. That's why they get a range in the grey there. And if they just run their model with natural forcings, so changes in solar irradiance and changes in volcanic forcing, you get this kind of result here. If you ignore the natural forcings and you say it's only greenhouse gas forcings, you get something like this. Okay, so you do start to reproduce this increase at the end here. If you add them all together, you get this result here, which most closely matches the observations. So the approach that's been taken here is basically by excluding individual forcings and seeing if they make the fit to data worse. Okay, that implies that having that forcing in place is important to understand the process. So in this case, because we have to have natural and anthropogenic forcings to get our data, well, to get our model runs to match the data, that implies that both of those things are important in determining the temperature rise. So we can do this on a global scale. We can also do it on a regional scale. So rather than just looking at the global temperature, we can look at the temperature records in individual regions, and we can see whether greenhouse gas forcing is impacting those regions at the moment. So what we've got here is the black lines are the observations. So you can see the temperature record for North America up here. Okay, so the temperature is black. It's been increasing since the 1950s up here. And if we ran a model with just natural forcing, we'd get the blue line and there wouldn't be much temperature change. But the red line shows that more closely matches the observations. Okay, so this is further evidence that we need to have greenhouse gas forcings in our models to faithfully reproduce the regional pattern of climate change as well as the overall trend. Okay. Okay, so how do we build these models? So we saw at the beginning of kind of my part of the course, we built up a very, very simple kind of climate model. And effectively, all of these kind of fancy pants climate models, what they're doing is they're doing that very similar thing. They're balancing kind of the energy coming into the Earth and that going out, and how much is being absorbed by different parts of the atmosphere. But they're also allowing kind of basically dividing the Earth up into lots and lots of grid cells and allowing matter and energy to move around between those grid cells as the atmosphere circulates, as heat is exchanged between the atmosphere and the ocean. But if we want to use those kind of models, I guess just like the model that I showed you at the beginning, which has got these kind of large-scale circulation patterns in it, we need to give it some parameters to start off with. So if we want to model what the future climate's going to be like, we need to tell it what the future carbon dioxide concentration is going to be. So there are two ways of doing that. So in the in the past, I guess maybe 10 years or so ago, for the Intergovernmental Panel on Climate Change, IPCC kind of reports, the approach on the left was taken, okay, where we basically chose a bunch of policy decisions. We're going to burn this amount of carbon, we're going to burn this amount of carbon, this amount of carbon, this, to basically give us a range of possible futures, okay? And then from those emissions, from that basically economic activity, we worked out how much CO2 that would result in. So if we had an economy that was kind of such size and it used so many tons of CO2 per GDP, that would give us a radiative forcing, and that basically gives us a parameter to put into our climate models, and that allows us to work out future temperature, future precipitation, all those things, and then we give it those outputs of the model to social scientists, and they work out if the climate changes by so much, what will the impact on society be? Okay, so that's the way it used to be done, okay, but we don't do it that way anymore. Okay, so rather than start out with a fixed set of basically policy decisions, we start out with some arbitrary amounts of radiative forcing. So are we going to kind of force the climate to be very warm, not so warm, try and keep it at the same temperature? And then we use the models to work out what emissions are required to meet those radiative forcings. Okay? And then that then feeds into an economic model that works out what kind of economy do you need to have to meet those those concentrations of gases, and then how that links into how we adapt and what the impacts of that are. Because the impacts on society will feed back. Okay, so if we kind of have lots and lots of climate disasters, that will impact our economy, which will then impact our carbon emissions. So this is important because it allows us to make decisions in the basically political decisions in the modelling world that will then impact back on our climate forcings. So so this is from the old way of doing it, but this is the kind of way that we have to go about this. We basically have to think about looking into I think you've got these tables in your, at least some of these tables. You basically have to think about what the world population is going to be, okay, and then what the economic activity of that population will be in terms of like money, how much money is that person going to make, and then also the energy intensity. So for each kind of pound that each person earns, okay, how much carbon do they need to burn to earn that pound? Okay, so that's kind of the energy intensity of the economy, and that's a kind of a political decision, right? Do we want to have an economy that's fossil fuel intensive, or an economy that's kind of like not fossil fuel intensive? And this is quite a hard thing to change, how our economy kind of works. Okay, even if we're going to have lots and lots of renewable energy, but we still have to make stuff. So we might have to have our stuff made in China, where they're still burning a lot of fossil fuels. So that's kind of like exporting our emissions to China. And from these kind of numbers, we can basically come up with climate forcings in terms of amounts of gases that are emitted. Yeah, I'm not going to talk about that one so much. But the result of these things are, so in the terms of modelling the emissions, okay, so we basically have, going from now into the future, we have a bunch of different scenarios that have carbon dioxide concentrations associated with them based on a model of our economic output going into the future and how our kind of economy will be, how carbon intensive it will be. We also have, we model those for each of the climate relevant gases. So for CO2, for methane, I think also for nitrous oxide. So those are all predicted to go up into the future. And then from those, we're able to produce a radiative forcing going off into the future. Okay, so that's adding up all of those effectively greenhouse gases. So that's using this method. If we use the kind of the other method here, we basically start out with this. So this is our initial starting point where we basically, for the end of the century, we choose that we're going to get some radiative forcings that are 8.5 watts per square metre, 4.5 watts per square metre, 6 watts per square metre greater than pre-industrial. And we kind of arbitrarily say how we're going to get there. And then from that, we basically then can model what our economy would have to be to meet these different scenarios. But with both of those approaches, we can basically use that radiative forcing and the concentrations of greenhouse gases to look from now into the future and how much warmer it's going to get, okay, for each of these different emissions scenarios. So this tells us basically if we choose to have an economy that will result in this kind of emission scenario, an RCP, representative concentration pathway 8.5, it will get this warmer. Well, so by the end of the century, it'll be maybe 4 and a bit degrees warmer. Okay, I guess this plot's quite important because most people, when they were talking about, you know, our different options as a society for climate change into the future, give numbers for what happens at the end of the century. Okay, time does not stop at the end of the century, and neither will climate change. Okay, so for some of these scenarios, you get to the end of the century and then it keeps on warming a lot more. This would be extremely unpleasant. 8 degrees C warmer than present, but that's in 2030. 2030, that would suck. 2300. Yeah, buy a house on a hill. Anyway, so we basically have these choices to make, and they end up with different temperatures at the end of the century. So it's not just the average. We're also interested in the regional patterns. So these are the expected climate change at 2030, roughly. So this is 2016 to 2035, and these are at the end of the century. And you can see that actually the climate doesn't really matter which emissions scenario into the future we pick. If we're worried about the climate in 10, 20 years' time, they're all pretty much the same. It's only once you start getting out to kind of, 85 years into the future now, we really start to see a difference between our kind of emissions choices. So choices we're making now about what kind of economy we're going to have, how much carbon we're going to be burning, won't matter for the next kind of 20, 30 years or so, but will matter for the future. Okay? And that's largely because all of this climate change has effectively already happened. That's climate change that has happened due to and will happen due to the emissions that are already in the atmosphere. Whereas this is due to emissions that will largely be in the atmosphere through our activity in the rest of the century. And you can see that the impacts are not uniform. So we get much more warming over land areas than we do the ocean. We get much more warming in the high Arctic regions than we do over other regions. So we do get this really different spatial pattern with warming. Again, it's not just warming we're interested in. Actually, the precipitation pattern change is probably more important than the temperature change. So here, the blue are regions that are going to get wetter. On average, the browny regions are places that are getting drier for the different emission scenarios at the end of the century. So once again, if we have the lowest possible emissions scenario from now onwards, the precipitation is not going to change so much. It's going to get a bit wetter on average. But if we go to our extreme case of kind of sometimes referred to as business as usual, or let's burn all the coal we can find, you can see regions like the Mediterranean, North Africa, Middle East, kind of places like that, are going to become a lot drier. So that's going to make those places a lot less habitable for people that like to drink water and grow crops and things like that. Other places maybe might get a bit wetter, so it might be good news for people living in the Sahara. Although if it starts raining a lot there, it's going to just wash away all the sand. Yeah, so again, Arctic's going to get a lot wetter. So that basically with the precipitation, it's not just a case of the whole world getting warmer, there's going to be big spatial differences as well. Right, so we've talked a little bit about it getting warmer, it getting colder. But that, a kind of a human level, doesn't really matter. Okay, if we think, well, it's going to get maybe 3 degrees warmer on average. I think if it was 2 or 3 degrees warmer than it was yesterday, we wouldn't really notice in terms of the average temperature. Okay, but what will matter is the extremes. So when we get a heat wave, okay, when we get an extreme storm, okay, when we get lots of flooding. So these are the things that actually matter to people in terms of whether their house gets washed away, whether their granny dies in a heat wave, these kind of things. So this was, yes, this happened in 2015. 700 people died in France because of this heat wave. Okay. Now, the heat wave itself, not maybe something directly to do with climate change, because sometimes it's just hot. Okay, you have a couple of days where it's hot, a couple of days when it's cold. So this is the kind of this is some data that I scrambled to get off the internet yesterday. So this is the Central England maximum annual temperature. So for every year since kind of 1850 or whatever it is, what I've done here, I've just noted down the warmest day of the year. Okay, so sometimes the warmest day of the year is really cold. Okay, 17 degrees C. Okay, sometimes the warmest day of the year is really hot. Okay, usually the warmest day of the year is somewhere around 23 degrees Celsius in central England. Okay, but sometimes you get a really hot one. Okay, and it's actually this is the thing that does the damage, right? It doesn't really matter if we move the average kind of warmest day of the year a little bit warmer. Big deal. But if we change this end of the distribution, that can have a really, really big effect. Okay, so it's this kind of extreme hotness can have a serious impact on people's lives. And this is kind of in a little bit more kind of schematic way, is that the mean of any event happening. Now this could be the average, well, not the average, this could be like the hottest day of the year, or a period of extreme wetness, like the wettest, the most amount of rain in a specific area in a given year. And that would either be close to the mean value, or sometimes you might get a very, very wet year, sometimes you might get a very, very dry year. Okay, but it usually goes around this kind of mean like this. So what happens if you change the kind of the average? So what happens if you change the average? You shift the whole distribution over one. So if you have some threshold above which, if a particular day is hotter than this, it will kill some people. Okay? Well, if you shift, if that was just this little bit of the distribution here, and it was kind of very, very unlikely, if you just shift the whole distribution over a bit, that's getting hotter than that same temperature starts to become a whole lot more likely. Okay? So if you shift the average, then you get a much higher likelihood of there being an extreme hot event. Okay? Or if this distribution was wetness and you shift the average wetness to being wetness, more wet, then you increase the likelihood of getting an extreme flood event. Or if you shift it towards being drier, you might increase the chance of getting a drought. Okay? So shifting the average is not important for the average, but it is really important for shifting the extremes of these distributions of weather. And it's not just shifting the average. If you make the distribution flatter, so if you basically make it more variable, if you make the climate just less predictable, then that will also increases the probability of having these extreme events. Okay? If you do both, then it's kind of like a double whammy. You shift the average and also change the variability, then you get much more likelihood of extreme events. So this is quite a tricky diagram to get through, but this is basically predicting the outcome of this change in likelihood of extreme events into the future. So if we just look at the graph on the left here, this is left, right? My right, your left. So in 1980, there's a 10% chance, okay, that a warm day the warmest day or whatever will be warmer than the 90% kind of range of all of the warmness of the days. So basically, if we just flip, we've got the little thing here, haven't we? Ooh, back we go. Back we go. So basically, if we've got this distribution of kind of like the warmest day of the year, okay? So we've got basically a 10% chance in this little window down here, okay? Maybe a little bit more, okay? So there's a 10% chance that we would be in this window down here, and a 90% chance we would be somewhere in the rest of the distribution. Now, if you look into the future, the likelihood of being above that temperature in any one year, okay, seems to increase, okay? And if we choose our most extreme kind of climate scenario of RCP 8.5, so this is the kind of burn lots of coal, we can see that we've got a 60% chance of having an extreme warm every year, okay, each year, sorry, rather than a 10% chance. So our likelihood of an extreme event has gone up by a lot. Okay, it's gone from 10% to 60%. You can do the same thing with precipitation. Okay, so instead of looking at the likelihood of exceeding a certain value in terms of temperature, what we're looking at here is the return period. So kind of when we have a storm on the news and say, oh, this was a 1 in 100 storm, 1 in 100 year storm, or a 1 in 50 year storm, this was really unexpected. This is what we're kind of looking at here. So we're looking at if you take a return period of an event, say a 1 in 20 year kind of wettest day, okay? If we look at how that will change in the future, as we go forwards into time, it becomes basically, say when we get to 50%, which will be kind of up here, that means that we'd now be at a 1 in 10 year storm. So we've basically increased the likelihood, or basically the return period of that storm by shifting this mean state towards being more wet. So that's what we can see on these maps. So what these maps are these percentages at a particular point in time at every point around the globe. So you can see here we've got the future temperature change, and basically the return value in terms of a graph like this is how actually we can just do this one here, the precipitation. So you can see that if for every grid square on the Earth, they've gone and so for every amount of storminess, they've worked out what the strength or the amount of rain you would need to get the strength of storm that could be described as the storm you would get every 20 years. Okay? And then they've seen how much that will change into the future. So in these kind of blue regions, okay, we'd expect instead of seeing every 20 years, we would see it every 2 years. Okay, so that's a massive increase in the wetness of these regions. Whereas in other regions, kind of down here, they stay at once every 20 years or get longer. So they get the likelihood of these extreme events goes down, or it gets drier. Yeah, so that's explaining this. So in these regions, we're looking at a 20-year return period, so the wettest day every 20 years. But in the future, how that degree of wetness, how often will that happen? So it'll happen in these yellow regions kind of every 6 years. So we've basically increased by kind of a factor of 4 or 3.5 how likely it is we're going to have extreme flooding in the UK, whereas in kind of some of the kind of drier Sahara type regions, it's going to be either the same or drier. So these are kind of these kind of, I guess, human relevant impacts that we're likely to see into the future. So we're going to get maybe warmer and fewer warmed. It's going to get warmer. And we're going to get fewer cold days. And this column here is basically looking at, has that already happened? Do we already see a change in our average weather in that area? And this next column is basically, is this our fault? So if you basically run a bunch of climate models and exclude anthropogenic CO2, do the climate models reproduce these kind of local effects? Okay? And then the last column is, in the future, will this carry on happening? Okay? And you can see for almost all of these things, so heavy precipitation events, droughts, increased hurricanes and cyclones, these are all likely or virtually certain to happen in the future. Okay, so looking a little bit more about some of the impacts of this stuff. So sea level rise. So again, it's not really the mean sea level rise that is going to be damaging. It's the small amount of sea level rise on top of the variability you get with storm surges and tides and things like that. So it's basically the extreme kind of variability in sea level rise, in sea level, and the changing the mean state a little bit increases the likelihood of breaching sea defences and having this kind of thing go on. So just to look and put this in context, so this is some evidence from the last glacial maximum. So this is kind of geological evidence, so 20,000 years ago to modern. So these are mostly estimates of fossil coral reefs. They kind of give us these tie points for sea level. And we can see that there has been large changes in sea level in the past, 100 meters or so. But the Holocene, the last 10,000 years or so, not so much. And if we look at what's happening now, so from direct measurements of tide gauges and also from satellites, we can see this nice consistent warming, or sort of consistent sea level rise that's going on over the last century. Different scale, obviously, this is meters. This is now millimeters, so we've only gone kind of 20 centimeters so of sea level rise over the last century. And we can say, again, just like with temperature, is this anomalous? So we can look at, so this is that temperature reconstruction again from proxies and then modern measurements. So this is kind of, is this bit anomalous? And we can then look at our sea level curve, and that's what this is kind of shown here of basically all these boxes are estimates of where sea level was in the past. And we can see from kind of, so the time on the bottom of this one is in years AD, so 0 here, and then kind of year 2000 up here. We can see that the rise we're getting now hasn't really been seen over the last 1,000 years. And in fact, there are other records that go back a little bit further now to say that it really hasn't been seen for a very long time. So the sea level rise we're seeing now is unique. And if we model this into the future, okay, so these are again our different emission scenarios based on kind of like burning lots of coal, not burning lots of coal. And sea level is expected to rise into the future by maybe up to a metre by the end of the century, but it won't stop at a metre, it will carry on going up. Time doesn't stop at the end of the century. So what these graphs over here are the reasons why sea level will carry on rising. Okay, so this is the expected sea level rise for different emission scenarios, and then these are the reasons why. And these are mostly this red line, so that is the biggest contribution to sea level rise, and that's just because if you heat up the planet, water gets warmer and expands. Okay, so we're not adding much water to the ocean from melting ice, just water, when it warms up, gets bigger, and sea level will then rise. We are also taking water out of glaciers, so that's the light blue line, and a little bit out of the ice sheets. Okay? But the thing to realize about these model projections is that they only are looking at basically gradual melting of the ice sheets. So these are some ice sheets. And actually, it's thought that these can become a lot more unstable than they are in the current set of climate models. So we might, in fact, see more contribution from melting and collapse of ice sheets than just the thermal expansion of water into the future. So the estimates we have for sea level rise into the end of the century are probably a bit of an underestimate. Just some impacts. So if we take a sea level rise of 1 to 2 meters, so this will be looking forward to the century, the next century rather than the one we're in now. So large parts of London underwater. This is kind of Cambridgeshire underwater. So there aren't many places in Scotland where it matters, because Scotland's got quite steep sides. But this is one of the probably most economically important areas of Scotland. So this is the Grangemouth chemical works. and that would be in trouble. So it's not just where people live, it's where we have our infrastructure that's important. And this down here is on the south coast of England, so this is Dungeness. So we've put a nuclear power station there, built on sand and gravel. But anyway. So again, it's not just us. A huge amount of the population of the Earth lives in these red regions, in the coastal regions of South Asia. So this is going to become a really big problem in kind of 100 years' time or so, because all of these cities are going to have to move. Okay, so basically what we're seeing now in terms of temperature, in terms of sea level, is unique, and it's our fault. And it's our fault because of CO2. So we have, CO2 is basically, it's definitely not natural. Okay, so this is where we are now. This is probably where we're going to go. This is just crazy. So this is a map of the CO2 in the atmosphere, a combination of observations and modelling, and you can see that, well, basically there's a lot more in the northern hemisphere than the southern hemisphere. You can see the different sources of maybe biomass burning here, lots of industrial emissions up here. So most of this increase in the northern hemisphere is actually because you get much more photosynthesis and then respiration and decay on an annual seasonal cycle. So in the southern hemisphere, so this is north, south, this is time, and the concentration of CO2. So it's going up over time, but there's a lot more variability in the northern hemisphere. And we'll go on to discuss that in the biogeochemical things later on. But basically, this is the story. This goes up, climate gets warmer because of this term here. So there has been some kind of news type things going, oh, yay, look, our emissions are coming down. So one of these things, basically, have we stopped emitting CO2 where emissions are starting to decline? Have we had our peak in CO2 emissions? So if you could kind of plot it up, you see that this is where we are now. Oh, it's maybe starting to come down a little bit. So this is basically an expanded version of that, and you can see that this is our cumulative, and this is our emissions per year. So gigatons of carbon per year. You see that's been increasing throughout the 20th century, and you can see that we do have periods where we reduce our emissions. Okay, they're usually when bad things happen. Okay, so we have massive depressions, world wars, oil embargoes. More wars, we reduce our emissions, okay? But this is really important. It doesn't matter, because this is the graph that climate matters for. It's not the rate of emissions, it's the amount of stuff that's in the atmosphere, okay? And this graph is only going up. So even if we keep our emissions at the same level, this will carry on going up. And this is what matters it's the carbon dioxide that's in the atmosphere, not the rate at which we're emitting it that matters. So if we want to bring this down, that is a massive task of geoengineering, okay? Or waiting for thousands of years, whichever you want to do. So I'm kind of finishing this set of lectures on a bit of a downer. But it's kind of exciting in that this is kind of it's going to be an active set of problems for you guys to kind of address through the rest of your degree, for the rest of your careers, kind of dealing with the problems that this is going to cause, maybe trying to actually do something about some of these gases in the atmosphere, which is what you're hopefully going to be doing something with. So summarize this lecture, kind of that stuff. Which you can kind of read. You've got summaries of it in your handouts. Right, so that's the end of this. So next week, I think Brian is going to start lecturing on chemistry on Tuesday, and then we'll carry on lecturing, except we might have to have one of my lectures for the biogeochemistry slotted in on Thursday, because Brian's got an appointment somewhere else with a hairdresser or something. I'm not entirely sure. But, right, so I will see some of you on Tuesday for the practicals. Go directly to the place where you should be having your practical. You should be able to figure that out from Learn, I think. Yeah. Have fun at the, have a read of the, not a read, a watch of the video, the exam video. Do that. And if you have questions about stuff, post them on the discussion forum. And if you want to have a go at answering the questions on the discussion forum, answer them on the discussion forum. Okay? Have a good weekend.